Hi, I'm Alan, and I will guide you through the poster titled Finding Geometrically Concise Representations of Homology. This poster is based on joint work between Nella Blazer and myself. Homology let us count how many d-dimensional holes there are in a space. This is very useful when you want to tell spaces apart, because spaces with different holes are also topologically different. For instance, a homology would tell us that the circle contains a one-dimensional hole, while the sphere contains a two-dimensional hole. Meanwhile, the surface of the torus contains a total of 3 distinct holes, one two-dimensional cavity and then 2 more one-dimensional holes, one of them going around the handle of the torus and the other one going around its center. We can use this to conclude that these 3 spaces are all different. Of course, we knew that already, but the power of homology is that it can be computed for any space of any dimension. This allows us to analyze spaces that most people have next to no intuition about whatsoever. Despite this, we know also that homology is not a perfect tool. For instance, if we attach a pair of circles to a sphere, like we did in the bottom right corner here of this picture, we get a space that have holes in the same dimensions as the torus. Homology is then incapable of distinguishing these spaces on its own, even though they are obviously different. One way we could have dealt with this issue is by finding the location of the holes that were spotted by homology. The problem here is that homology does not have any preference about which representations we should use for a given hole. So, for example, all 4 circles indicated in this deformed cylinder are all equally good descriptions of the hole as far as homology is concerned. Although for us, the natural choice of representative would probably be to pick the geometrically smallest one. And then by smallest, we mean the shortest one, or the one with smallest area if it was a two-dimensional hole, or more generally, we would just say that the smallest is the one with the smallest volume. It turns out that it is very hard to compute the smallest representative of a hole. More precisely, Chen and Friedman showed that to find a constant factor approximation to an optimal representative of a hole is NP hard. We have also proved that it is W1 hard to find constant factor approximations if we parameterize the problem by solution size. Roughly speaking, this means that even when we know that we are looking for relatively small holes in the space, they are still pretty difficult to find. The good news is that we have also found a parameter that actually does help us to design efficient algorithms, and this parameter is called tree width. Tree width is one of the really big hammers in parameterized complexity theory, and it is a notion that tries to capture how close a graph is to being a tree. The actual definition of tree width is rather technical, so we will skip it here, but we want to show you the intuition behind the notion with this picture here to the left. So in this picture, we want to say something about what the tree width of the topmost graph is. As you can see, we have covered its vertices by a family of sets, and these sets, in turn, we've made into a tree in the lower figure. And this tree has to satisfy certain critical criterions. The idea is that if the family of sets contain only small sets, the tree width of the graph is also small. But we work with spaces, not with graphs. So how can we apply tree width to our setting? Well, graphs are everywhere in computer science, and that includes in topological spaces. More precisely, we represent our spaces as simplicial complexes. This means that our spaces are made up of points, lines, triangles, tetrahedra, and n-dimensional tetrahedra. We can therefore track information about how these building blocks are glued together using different graphs. We have looked at 2 graphs in particular. The one is the topmost blue graph, which generally tends to be smaller but which have a higher tree width. And then there is the lower graph in red, which is bigger but can have a smaller tree width. Using the tree width of either of these graphs as a parameter, we have discovered and implemented 2 different parameterized algorithms for finding the smallest representatives of holes. Both algorithms has a guaranteed runtime of 2 to the O of k times n where n is the input size of the problem and k is the tree width of one of the graphs we just discussed. You can see how their implementation performed compared to one another in the plot here to the right, and it should be clear that the algorithm based on the red graph was much more efficient than the blue graph, at least on test cases where the problem wasn't solved immediately. Despite the significant difference in runtime when implemented, both algorithms are actually ETH optimal. This means that unless the widely believed exponential time hypothesis is false, it is only possible to make better algorithms that improve the number in the base of the exponent in the runtime of these algorithms. To prove ETH optimality, we used what we suspect might be a completely new kind of ETH reduction, or at least a new technique. And it goes from the problem called max cut, parameterized by tree width, where we already have lower bound given by the ETH, and it goes to our problem. The idea is that it takes the graph in the instance of the max cut problem and maps it to a space in such a way that the space, if the graph had a low tree width, so does our space. Finally, I would like to say something about a few selected open questions. First, the ETH optimality result roots out algorithms that are strictly faster than 2 to the O of k times n, but it does not say how small we can make the base of the exponent. Currently, the best of our two algorithms run in 4 to the k times n to the c time, and we have reason to believe that this base cannot be improved below 2. But it is not clear to us if the theoretical limit on the space is 4, 2, or if it's some number in between. Second, we are also wondering if we can solve the same problem on more general complexes, such as CW complexes. Or we could take a big picture view and start to think about which other parameterizations we should look at for this particular problem, or to think about which other techniques from parameterized algorithms we can apply with success to this problem, or indeed to any other problem in computational topology. And that's it. I hope you enjoyed this video. If you have any questions about the poster or about this research, then you must feel free to contact me directly or to leave a comment in the comment section of this video. To see the preprint of the paper that this poster is based on, or to get a digital copy of the poster, or to download our code for this project, please use the QR code at the bottom right corner of the poster in this video, or have a look in the description of the video where I will put a link. Thank you so much for watching, and I hope to see you around.